Hi. Hello, hope everybody is well. So here we are back again, and I'm looking today to do, let's see, it is question 3.20 D, E, and then 3.23 A, B, C, and 3.24. So I'm going to ask you to do, where's my notes here? I'm going to ask you to do questions 3.20 E and 3.23B. So 3.20E, here we go, 3.20E and 3.23B, Baker, that one there. Okay, so here we go. I'm going to start in. Starting in with question 3.20D. And I'm going to try just doing this on a piece of paper and seeing how it goes. So 3.20D says if the composition of G and F is onto, then G must be onto. So let's have a whack. Before you do these, of course, sometimes it makes sense to have a little bit of scratch work on a piece of paper. So so I'm going to write down a picture for composition. This, of course, isn't a proof, but it is a picture. So I have two functions composed together. Here. And looking to do G circle F. So this is going to be G, and this is going to be F. Okay. And I don't know, just to draw some stuff here. Just some dots. I don't know. I don't have any particular idea in mind. I'll just draw some arrows. Okay, and some arrows. But I'll make G be not onto. And see what goes wrong. Okay, well, the composition takes this first dot over to this first dot over to this first dot. The composition takes this second dot over to this first dot over to this first dot. Composition takes this third dot over to, I don't know, maybe I was going to the second dot, I'm not sure, over to the second dot. But there's no way, if G is not onto, there's no way to get that dot. So if G is not onto, then doing F first and then G can't possibly be onto. If G misses a dot, then F first and then G has to miss a dot. Okay, so that's the idea. So let's see, the question is 3.20D. 3.20D. All right, so I'm going to suppose for contradiction. That G is not onto. Okay. Then there is an element of G's codomain where no x in the domain of G maps to Y. Okay. Well, if no x in the domain of G maps to Y, why then it's necessarily the case then that for any A in the domain of F, F of A followed by G, so G of F of A followed by G, you can't possibly map to Y. Then for any A in the domain of F, we have F of A equals X is in the domain of G. But then G of F of A is not equal to Y. because we just said no x maps to y. And this contradicts that G circle F is onto. Okay, so this is one of those deals where you write down a picture, sometimes two, sometimes three, sometimes you don't hit the right thing right away. But you write down a picture and it gives you the idea that of what can go wrong, and then you just say, well, it's not possible to have this set up. That's all. That's all. So, of course, a person can walk around sometimes for a couple hours. What is going wrong? I don't see it. But in the end, it's always, those are more satisfying to get when you get them. Sometimes you don't get them, but when you do get them, they're more satisfying. That's part of the fun of math. Okay, I mentioned that I'm going to ask you folks to try question E. It's actually two separate questions. G circle F is onto, must F be onto? If G circle F is 1 to 1, must G be 1 to 1? And you either have to, if you say yes, you have to prove it. If you say no, you have to prove the no, which is you have to give an example of a no. So give an F and a G, domains and codomains, and that gets you a no. And I will say that sometimes in mathematics, coming up with counterexamples is tricky, but I don't believe there are any in this entire book where it's one of these counterexamples where you say, I worked on this for hours. So a person often goes back and forth. Well, maybe it's true, but no, I can't get it to work. I can't get a proof to work, so I bet it's false. But I hope that a person is not feeling that I worked on that for hours and hours and hours. It should come reasonably quickly. Easy for me to say. Anyway, next up, I'm asking. So I did D. I'm asking you to do E, and then there's a couple definitions for the identity function and also for inverses. Inverses prove to be one of the trickiest things that we do. So I have an exercise here immediately following the definition of inverse. I have an exercise here that asks the person to work with a couple of examples of inverses. It proves to be the case that that folks find inverses a little tricky, and indeed inverses are a little tricky because it's like the difference between multiplication and division is that it's very easy to multiply, very easy to go forward, but if somebody says to you, find a number that divides 7,239, you're like, oh. So it's a little harder to go back. And sometimes indeed you can't go back. So 3.23 I hope gives a person a few examples of inverses. So I intend to do, let's see, I'm going to ask you to do part B, and I intend to do A and C. So let me give A a whack and see how it goes. Okay, so let's see. The first definition is that the identity function is the one that has the action where identity function on a domain element just simply returns that domain element. So it acts in some sense like multiplication by 1, or it acts like addition with 0. Is that it in some sense doesn't do anything. Okay, so it is in some sense a null operation. All right, and then if G circle F is the identity function, then G somehow cancels out F. So like you think dividing by 7 cancels out multiplication by 7, and subtracting 9 cancels out adding 9. So these two things somehow cancel each other out. But there's a little trick there. It says left inverse, right inverse. So if G circle F is the identity function, then G is called a left inverse of F. So there's something, that's a clue that there's something a little tricky here, that something can happen on one side that doesn't happen on the other side. And indeed, that's the whole, you'll see that in these exercises. So if G circle F is the identity, in some sense G cancels out or undoes F. Why then G is called the left inverse of F. G cancels out F from the left when acting from the left. And again, that's a lot of times the words are a little bit of a clue. The word here is a clue that it's not as straightforward as adding 7 and subtracting 7. That sometimes more complicated things can happen, and of course I have examples here. And then finally, if G is both a left and a right inverse, that's the plus 7 minus 7 case, then it's just called an inverse, or sometimes for emphasis you might say a two-sided inverse. And you would denote it with F superscript minus 1. There's some possibility, of course, of confusing F superscript minus 1 with 1 over F. But the inverse operation occurs much more often than the 1 over operation in this context. So usually it means inverse. Okay, anyway, so 3.23a, let me see if I can bring it to a spot where I can read it. Come on, come to Papa. There we go. 3.23, I have a little trouble reading it on the screen here. 3.23a says, let G map R3 to R2 be the projection map that just takes x, y, z and projects it to x, y. So it squashes things down to the x, y plane. And let F from R2 to R3 be the injection map that goes from the xy plane to xy0. So it takes you from 2-dimensional space to 3-dimensional space. It's called injection map. And it says then G is a left inverse of F, but not a right inverse. So let me try that one, and I'll get rid of the window, and underneath is the paper, and I'll write on this side here. Okay, so this is a 23a, 3.23a. And again, we have G takes R3 to R2, and you just simply take X, Y, Z. And again, you notice this, the arrow there is the whole function. The arrow with the little bar on it is one element at a time, so it sends it to X, Y. And F, in some sense, does the opposite. It goes from R2 to R3. So kind of calculus type functions, and it sends xy to xy0. Got a little trouble drawing 0. Not so good. Okay, and then all I'm asked to observe in question A here is that if you do it in one order, it works. If you do it in the other order, it doesn't work. Okay, so specifically, if we go from xy to xy0 and then back to xy, you're good. So suppose you go from xy to xy0 and then back to xy. Sometimes when you lose that third element here, sometimes when you lose that third entry, sometimes that's called the forgetful function, because you just forget about the third entry. So this, of course, is G, and this, of course, is F. And exactly what you see here is that G circle F of some input, x comma y, is just xy. So G is a left inverse of F. And the question asks me to check it in the other direction, and when I do check it in the other direction, I get, let's see, x, y, 0 goes to x, y. Oh, I'm sorry, xyz, forgive me, xyz goes to xy, which is then sent to xy0. And now, here's the problem. If z is anything other than 0, I was trying to think ahead, which is always a mistake. If z is anything other than 0, well, that doesn't work. So F circle G, my goodness, making a mess of this. F circle G of, let's say, x, y1 is not equal to x, y1. Specifically, it's xy0. But in any event, it's not equal. So we have that acting from the left, G will cancel F. But acting from the right, G will not cancel F. So G is a left inverse of F, but G is not a right inverse of F. You can say it with F's if you like. Pardon me. F is a right inverse of G, but F is not a left inverse of G. If you like the F's better, go for it. So it works in one direction, but not the other direction. And that, of course, brings us back to the, pardon me, that, of course, brings us back to the definition. The definition was careful to talk about left and right because there's some left-right thing happening here. And so the example exactly shows, in a familiar calculus way, the example exactly shows what left-right thing is happening here is that you can have this thing not work in one direction, but does work in the other direction. So the sidedness makes a difference. Okay, and of course I mentioned that I'm going to ask you to do here, this one here, I'm asking you to do B, right? 3.23b is what my notes say. So I must be doing C and then 3.24. Okay, let me have a read here. So C says D is 0, 1, 2, 3, and C is 10, 11. I just like to have them not share any elements, just so that nobody ever says, which of the 7s is that? So these are distinct from those. That's all, disjoint sets. And then I gave a function, and I said show that it has more than one right inverse. Okay, so let's see if we can make out what's happening there. Oops, I forgot to uncover the thing. There we go. See if we can make out what's happening there. Okay, so the set D, the domain, is, oops, this is 3.23c. 3.23c. So the domain D is 0, 1, 2, 3. And the codomain for the function f is 10, 11. Okay, and I have, of course, f takes d to c. Oops, darn it. Making a mess of things today. F takes d to c. This is just a cross out, I'm sorry. F takes d to c, and it gives you a specific, so the even numbers map to 10, and the odd numbers map to 11. And now the question, of course, is about canceling f. So canceling f works in the other direction. And it says there's more than one way, there's more than one function that cancels f, more than one right inverse. So a right inverse, of course, would be f circle g, and g is a right inverse of f. On the right, it acts to cancel f. G is a right inverse of f if you have this for all the x's in G's domain. Okay, so I got to figure out where to send 10 and where to send 11 in such a way as to make this equation come out true. Again, where to send 10 and where to send 11. So where to send 10 and where to send 11, where does G send 10 and where does G send 11 in order to make this equation work out. So here I go. It says there's more than one, so I'm going to write down 2. I'll call this one G1 and I'll call this one G2. I guess it seems to me that if you send 10 over to 0 and 11 over to 1, then, for example, plugging a 10 in for x, g of 10 makes 0, f of 0 makes 10, that works. Plugging an 11 in for x, g of 11 makes 1, f of 1 makes 11, so that works. And then over here, I just have to do something different. And you could send, for example, 10 to 2. Great. You could send 11 to 3, but just to illustrate that you could do a number of different things, I'll send 11 to 1. And again, does this equation work here? So let's try it. G2 of 10 is 2. And 2 maps back to 10. F takes 2 mapped back to 10. G2 of 11 makes 1, and F takes 1 back to 11. So that's right. So these are two different right inverses of F. One thing that you see that we saw some of in this class, but maybe not enough of, at least till now, is that the question asks me to show that something is true, that something exists, show that there's two right inverses. And the simplest way to show that there's two right inverses, not necessarily the only, but the simplest way to show that there's two of something is to exhibit them. The simplest way to show that something exists is to just produce it. So I took out a paper and I started drawing arrows and thought, what is it that the question asks me to do? The question asks me to come up with f circle g of x equals of x equals x, the question asked me to come up with f circle g of x equals x, and I just tried some. Okay, so one of the things that I try to emphasize in this class, especially as we approach the end of the class, because it comes up more at the end than the beginning, is that in calculus, you typically just kind of flip back and find an example that looks a lot like the question you're being asked to do. That's great. That makes all the sense in the world in calculus. But as a person moves through the program, the idea is that you're supposed to be supposed to be developing into a more and more independent learner, a less and less sort of a person who is spoon-fed this material. And so one of the things that we're trying to do, one of the things in this class and in later classes that we're trying to do, is to help a person's process of saying to themselves, what is it I'm asked to do? What might I try? Okay, I tried this, it didn't work. That doesn't mean I stop. It means I try something else, kind of stuff. So this is a good example of that. A person who's doing 3.23c is really asking themselves, what is the question? And this proves to be what the question is. Come up with a G that does this. Generally, for everybody in the room, I mean, sort of run your mental finger down the list of people in the room. For everybody in that room, once you come up with what the question is, coming up with G's that answer that question positively is not so hard. So the difficulty here is trying to work out, take those first couple steps of independence. They're not easy steps, but the first couple steps of independence where you're less and less being told what to do and more being helped to think through the issues for yourself. Okay, and hopefully over the course of 4 years, that's one of the things that we work on. Okay, anyway, enough blabbing. Time to get back to work here. So the last thing that I want to do is exercise 3.24. Again, I'm asking you to do 20 E and 23B. So the last thing I want to do today is 3.24, and so 3.24 is one of these three-parters, and it's often the case with these that pardon me, that the individual parts are not so hard. So it says F maps Z to Z is given by F of A equals A plus 3, and G maps Z to Z is given by G of A equals A minus 3. Show that G is inverse to F. And the thing that a person has to worry about here is that you have to show that G is a left inverse and also that G is a right inverse. So 3.24 Roman 1. 3.24 Roman 1 is that we have to show G is a left inverse and then in a second I'm going to show G is a right inverse. So G is a left inverse. I have to say G circle F of what letter is used? A. And that's G of F of A. I just put in some space just to help a person's eye get used to it. F of A is, what the heck is it? A plus 3? Okay, and in calculus, a person learns that G takes its argument and subtracts 3 from it. So just because it says G of A equals A minus 3 doesn't mean that, that you do some crazy thing with the A's. The two A's are unrelated, and so you get A plus 3. That's the argument to G. Take away 3, and of course everybody knows that that's A. And G is a right inverse. I think probably here we could say similarly, because everybody is not going to find this particularly a challenge, but I'll write it down. F circle G of A, and just to go a little quickly, this is a little more quickly, this is F of G of A. So that's F of G A minus 3, which is of course A. Maybe I'll just stop there. Okay, and that's it. So G is a two-sided inverse. It's both a left and a right inverse. That's it. So you just call it an inverse. Right? That was Roman 1. Roman 2 says where H is the function that returns n plus 1 if n is even and n minus 1 if n is odd. So this is 3.24 Roman 2. So where H of n is, it's n plus 1 if n is even, and and n minus 1 if n is odd. Then the question says find a function inverse to h. And of course, any question in this class, if it says names, it's just sort of, unless it specifically says otherwise, you're asked to justify the. So it says find one, but I'm of course would be asked to go through the argument, and I'm a little bit nervous about running out of paper here. We'll see how it goes. So if you take out a piece of paper and you start working with some values of h, what you see is that, for example, 2 goes to 3, and 3 goes to 2. 4 goes to 5, and 5 goes to 4. So they're swapping places. So the idea that a person would have for how do you undo swapping places is swap them back. So we will show h is its own inverse. There are some functions that are their own inverse. An example of a function that is its own inverse is in calculus if you look at positive reals and you look at 1 over x. Well, 1 over x takes you back to x. Okay, anyway, so first, this shows h is its own left inverse. And so I'll have h of n, and there are two cases. If n is even, then I'm looking at h of n plus 1 equals n plus 1 minus 1. And the opposite is h of n minus 1, which is n minus 1 plus 1, if n is odd. And of course, in either case, you get n. Now, I said that shows that h is its left inverse because there's h on the left of h, but obviously it also shows h is on the right of h, so that actually does it both. Now, you could say here, for example, similarly, h is its own right, or in the exact same argument shows that h is its own right inverse, whatever you like. So I'll leave that as just words to put in, and then we're done. Okay? So this inverse stuff, it's not brutally hard, but there's a couple things to think about. There's a couple things where a person says, stuff I never thought about with cosine and arccosine, square root and square, or tangent and arctangent, the e and log, these other inverse functions that I've run across in the past. Okay, and then lastly, the last one. So 3.23c. 3.23c says, it says S maps R plus to R plus. And S is given by x goes to x squared. Okay, and it says find the inverse. And again, as usual in this class, you can't just say the inverse is. You have to somehow justify it. Although the justifications that we give in this class are justifications to a particular audience, and because all writing is to an audience, and the audience in this class, of course, is peers. So a person doesn't need to start out with the Zermelo-Fraenkel axioms or something. You start out assuming that people know what they know, and so in this case, people know about squares and square roots and all this kind of stuff. Okay, so of course, to find the inverse of a square, the very first thing that occurs to everybody, everybody's taking calculus, and everybody thinks, well, you want to take the square root, but then the second thing you think is, but what about like negatives? Negatives can't happen. That's the point here. The point is that sometimes whether or not a function has an inverse depends on the domain and codomain. So if I put r there, and the non-negative reals, if I put r there, then the question wouldn't have an answer. So the domain and codomain stuff can strike a person sometimes as just sort of bookkeeping baloney, but sometimes makes a big difference. Sometimes. And here's an example. So the inverse of s is the square root function. So I'm going to write that down. But again, the audience is people in the class who have taken, so let's say calculus, linear algebra kind of stuff, and so folks don't need a whole lot of talking to about square root. So for a proof, I'm going to say something like the inverse of s is, and I'm just going to give it a name, f maps r plus to r plus. Notice that the codomain of s is the domain of f, and the domain of s is the codomain of f, because they go in the opposite directions, given by f of x equals square root of x. Okay, you can write it this way, or you can write that. I don't care. It doesn't make any difference. Okay, now again, everybody in the room has experience with square root, so all I need to do is caution a person here something about negatives. So note that the domain of f includes only positive values. Positive values. And that if you take the square root of the square, that one's not going to, not going to work for negatives, but there are no negatives, as well as if you take the square of the square root. Okay, that one would work for both directions. So it is a two-sided inverse. So again, here, all writing has an audience, but a person needs to make an argument, and the argument that we are expressing to the person who's reading it is that square root works because that's a plus. If it wasn't a plus, we'd be in trouble, but we're not in trouble because it is a plus. Okay, all right, very good. So again, I'm asking you to do number 20E, 3.20E, and also 3.23B. Okay, and again, I hope that everybody is well. I wish we were meeting together in class, but anyway, I hope that folks continue to do well, and that everybody is safe. Okay, very good. Bye-bye.